Thank you for that. Okay, so let's get started. We'll start off with a brief general motivation and overview of distributed techniques, specifically as they apply to inference. And then we'll go a little bit more into vLLM-specific decisions and architecture. And then at the end, we'll go into some Ray-specific topics as well. Okay, so what's really our motivation here for the talk, right? I'm sure like everybody in the audience has encountered this situation at one point, which is when your GPU goes out of memory, right? And nowadays, like models continue to grow beyond the memory of a single accelerator, a single node, and even you might need to use multiple nodes in some cases. And a really good example of this is Llama 4 or 5B, right? One of the largest models today, but at the same time, it's one of those models that most people want to use, right? But it can be quite challenging to serve for this reason. And the challenge for us is really how can we continue to effectively serve these models? And that's really a challenge for any inference engine out there, but we'll take a look at what's been done in vLLM specifically. Okay. So there's one solution here, right? Which is to just reduce the number of bits needed primarily for your weights, right? And nowadays, there's a lot of innovative research in this area. People have gone down to very low precisions. There's experimentation with 2-3 bits even. And this can be a good solution, right? But the challenge is that your accuracy is potentially affected, right? So you need to do a lot more work to ensure that your model is still doing what you want it to do. But at the same time, this also has like limited scalability, especially, for example, when we go from FP16, or BF16, I should say, to FP8, we're having the number of bits that we need, but then at the same time, you might still need like one node, right? 400 billion parameters is still 200 gigabytes, even at int4. So you still need, in that case, multiple accelerators. And so the solution to that really is, as I was alluding to, is to use multiple GPUs or multiple accelerators, right? And so there's a variety of ways that we can split models across GPUs, and that's what we'll be diving into today. And here, one way of doing this is to divide your GPU up layer-wise. So each of the layers themselves get split up, and a GPU takes up a portion of that layer. And this is from Megatron LM. Okay, I'll hand it over to Sangbin to cover the next portion.
Oh yeah, so let me quickly go over the differences between the distributed pre-training and also inference. So pre-training usually have very complicated parallelism, like you apply like 2D, 3D, 4D parallelism on it. But then generally, comparing to the inference, it has a less components. It usually, the commonly used something called SPMD architecture, which you just run the same code on all the workers. And there's no other components. For inference, usually it has more complicated architecture. For example, for LLM inference, it has a scheduler, and it has a KV cache, and for different techniques like speculative decoding, it can commit additional models. In terms of performance, training usually requires just the throughput because you just fetch a lot of input to your model to train, versus inference, you usually use both throughput and latency, like depending on what's your workload. For the scale, training typically has a very large scale for language model training. Like it's pretty common you can have more than 10,000 number of GPUs. Inference, usually you have small number of GPUs required, but then instead you replicate the instances instead of like scaling your model to thousands of GPUs. In terms of dynamicity, train usually has less dynamicity because you can know the inputs and everything ahead of time. But inference usually has more dynamicity because you don't know exactly what kind of prompt is going to be accepted ahead of time. Then let's actually dive into the problem and solution, like what kind of solution vLLM provides in large language model inference. So as Murali brought up in the beginning, the typical problem is your model cannot fit into a single GPU. And it's also possible your model cannot fit into even a single node. For example, if you serve the Llama 405B model, it requires 900 gigabyte of GPU on FP16. The biggest node available in the cloud is having like 80 gigabyte of GPU, 8 of them in one machine. So you cannot fit the single model in a single node. So you have to have a solution to actually distribute your model to multiple nodes with less performance penalty. Other issue we found from vLLM is that because inference has more components, the control plane, which is like scheduler or other components, their overhead coming from CPU actually harms the GPU utilization. So to solve it, vLLM supports tensor parallelism to shard models to multiple GPU in a single node. It also comes with pipeline parallelism, which shard models to multiple GPUs across nodes with a small communication overhead compared to tensor parallelism. And also, vLLM has an optimized control plane architecture. So let me go over how the vLLM architecture real quick. So it comes with an API server, which is an HTTP server that provides OpenAI compatible APIs. And once you get the prompts from the API server, there's a tokenizer that tokenizes your inputs. And the inputs are queued, and then vLLM comes with a scheduler, which keeps picking the batch and then sending to all the workers and get the result and keep repeating this process. It has an executor component, which basically manage resources. Like one example, they use Ray under the hood, and they also have a microprocessing-based backend. So this executor, the schedule the process, start the process, manage the process, as well as sending the inputs to all of the workers to run the model. And once you get the result from the workers, the sampled result is going to be going to the tokenizer, and the tokenized result is going back to the user through API server. Since it's the distributed inference, we are going to mainly focus on these three components today. Then actually, let's start from what kind of GPU parallelism, like how each different GPU parallelism works in more details. So the problem one was that model cannot fit into a single GPU. And as model gets bigger, one GPU is not usually enough. And then you want to scale your model into multiple GPUs. And the most common solution in a small scale is you're sharding your weights horizontally and compute each pieces horizontally, concurrently. There are two common techniques. The first thing is called tensor parallelism, and also another thing called sequence parallelism. Sequence parallelism is not supported at vLLM yet, but we're going to talk details. And we're going to mostly talk about tensor parallelism today. So this is how tensor parallelism works in more detail. It's the basically diagram that shows the MLP layer for Llama. In vLLM, so the MLP layer contains three different weights. If you look at their GitHub, it's called W1, W2, W3, but it's like gate and then up projection and down projection. In vLLM, you combine multiplication of gate and up projection, and then you multiply input with the first weights. And then you apply the activation function, which is MLP. It's because it's MLP. And then you multiply the down projection weights. So in this case, A and B is usually large because it's large language model. How tensor parallelism works is for the first two layers, you shard your metrics by column. And then you shard the down projection metrics by row. So this is how it actually looks like in two GPUs. So as I mentioned before, in the first weight, you shard the metrics by column. So if you look at the upper part, it has A1, which is the first GPU, and the A2 is sharded to the second GPU. And then you apply the activation function. It's the element Y, so you don't need to do anything here. And then you get the result Y1 and Y2. And if you look at the previous slides, Y1 needs to be multiplied to B1. And there's a typo, but Y2 has to be multiplied to the B2, which is the bottom part of the matrix. And you can see the Y1 and Y2 is already naturally split by the column, by the first gate up projections column-based sharding. And then, which means that you don't need any additional communication overhead here, and you can directly multiply to different row B1 and B2. And you get the result, and when you multiply, when you shard your weights by row and do matrix multiplication, you need to sum the weights to get the final result. So you reply the all reduce. So this is how you get the how you run the tensor parallelism on MLP layer. Then what's the trade-off? So as you can see, tensor parallelism shard your weights horizontally, and then you're able to run each of computation concurrently, so it can improve end-to-end latency. But because you have to do all reduce at the end of your layer, it requires the higher communication overhead. And usually, it requires the specialized hardware such as NVLink, which has much faster, which supports the much faster communication speed. And also, not just MLP layer, but attention layer also use the tensor parallelism. And for that case, it's sharded by the hedge. And one of tensor parallelism is that your hedge has to be divisible by tensor parallelized size, or you have to add the padding manually, which is a pretty tedious process. Okay, I'm going to pass back to Murali, and he's going to explain context and pipeline parallelism.
Okay, yep. So as Sangbin was alluding to earlier, like in vLLM, currently we support tensor parallelism. There's also a class of techniques. Some call it context parallelism, sequence parallelism, ring attention. There's various ideas out there. But essentially, the idea here is that there is a flaw with tensor parallelism, especially when it comes to the activations, right? In some cases, you still need to get the full activation on each GPU, but for long contexts, this is undesirable, right? So you have these class of techniques that allow you to basically shard the tensors along the sequence dimension as well. And so this is a way of extending tensor parallelism, replacing it with a much more scalable approach. Okay. And so we'll go to our next problem, which is multi-node inference, right? And so at the very beginning, I talked about Llama 405B, and at full precision, or I should say BF16, we have issued that even with the full node of H100s, it can't fit, right? So we need multiple nodes in this case. Of course, you can always go to FP8. That comes with its own set of challenges. Yep. And so the issue here, though, is that across nodes, tensor parallelism will result in a lot of overhead. And so that's something that we really want to avoid. And that's where pipeline parallelism comes in. And so the idea here with pipeline parallelism is we're really sharding across a different dimension instead, right? So we take a group of layers, and then each group of layers is going to be on a single GPU. And so you can see some code, this is exactly how we do it in vLLM, where we're using a send and receive paradigm to send from one accelerator to the other one. And on each GPU, we're just storing the layers that we need, and then the rest of the layers are replaced with this identity layer, or basically a no-op. Okay, and so there's some trade-offs here as well. One of the main advantages of pipeline parallelism is that it does have a much lower communication overhead compared to tensor parallelism. But at the same time, it doesn't actually improve end-to-end latency the same way that tensor parallelism does. And it's also prone to execution bubbles. And in general, the implementation is a lot more complicated than tensor parallelism. And so here, really, the solution is that you kind of want to use both of the techniques together. Maybe use tensor parallelism within a node, and then pipeline parallelism across nodes where it's more expensive. Okay, and in a naive implementation of pipeline parallelism, you might come up with some schedule like this, right? You go through all the layers, and then once the last GPU has finished its work, you again repeat with GPU 0, right? But this carries some obvious drawbacks here, which is the execution bubbles, right? We're wasting a lot of time with these GPUs. And so really what we want to do is something like this, right? Where we bring the executions, and we really have this pipelined fashion. The way we accomplish this in vLLM is we take like all the requests that we have, and these are split up into separate request groups, right? And once these are split up, then they're all scheduled together, and there's no cross-contamination. So this is basically what allows us to maintain data dependencies. But then at the same time, we have this challenge that we need to have multiple request groups at the same time. And the way we accomplish this is we actually launch 4 of these requests at the same time. So we have all 4 request groups here that are kind of bolded, operating at the same time. And we use locks so that we can reserve a GPU for the correct request group. And then you can see those last 2 request groups, those are going to be scheduled in the next iteration. So this is our strategy to implement pipeline parallelism within vLLM. Okay. And then there's another problem that you might have, which is batching inefficiencies, right? So in inference, as Sangbin was saying earlier, it's a much more dynamic workload where you might have pre-fills, you might have decodes, you might have a lot of requests at one time, or you might have few requests. And what you really want to do is ensure that that's still taken care of. You don't have these pipeline bubbles and imbalances coming from that. So we can leverage another technique called chunk prefill, which is already in vLLM, in order to allow us to kind of even this out and make sure that our pipeline is as efficient as possible.
Okay, so we are going to the third problem. The CPU becomes a bottleneck. So LLM inference has very high performance requirements. So typically, when you have Llama 8, like 8B model, and you have like 800 GPU, it can only take like 10 to 20 milliseconds or lower for generating a single token for multiple batches. So in this case, having the CPU can become a bottleneck to 100% utilize GPU of your engine. And there have been actually a lot of techniques to reduce CPU overhead across the board. We are only going to focus on one technique today that's relevant to Ray, but there are a lot of different things like CUDA graph, or they're currently working on re-architecturing the scheduler to be asynchronous, or many other different techniques are there, but we are only going to focus on one technique today. And then this also means that distributed architecture also should have low system overhead. Now let's actually go back to vLLM architecture last year, like around 2023. So the original architecture has this driver, which has the LLM engine class. This LLM engine class also contains a scheduler. So it chooses the group of batches, and it's sending data to Ray workers through CPU. And then each worker is preparing the argument, which means they're moving the CPU data into GPU and run the model together. So as I mentioned before, it's called single program, multiple data programming style. So you run exactly the same code with different data, with tensor parallelism in it. But the issue last year was that when they had this architecture, Ray usually have 1 to 2 milliseconds overhead when you're sending a task. And then there's additional serialization overhead because you have to serialize your CPU data like a large prompt. And then when you have really large prompts, like tens of thousands of tokens, and you have multiple batches, it's possible your serialization can take more than tens of milliseconds, which is really high for end-to-end overhead. So vLLM, they re-architected the control plane to use Nickel broadcast instead of Ray here. So basically how it works now is that your first worker, the rank 0 worker, coexist in the driver. So in this case, scheduler moved the data to GPU, and then the data that's moved to GPU is going to be transferred through Nickel. And then you're running all the workers at the same time. This architecture reduced the serialization overhead in general, but then it comes with other problem like model and control plane actually interrupting each other because they're in the same process, and Python has a GIL. So you actually cannot fully parallelize these two scheduler and the GPU workloads. So we try. So Ray has a new feature called Ray compiled graph. So we try to leverage this feature to solve this problem. So Ray compiled graph is the feature that mimics the Ray DAG API that already existed. So instead of the familiar .remote, you use the .bind API, and then you're able to construct the DAG this way, and then you call the compile API at the end. Compared to existing .remote solution, the compile graph has very low system overhead. So for example, the original Ray has 2 to 3 millisecond overhead to send a task to other task. With the compile DAG, you only have 50 microseconds overhead. And it also comes with direct GPU RDMA, so it uses Nickel or other communication primitive under the hood to actually support GPU to GPU transfer, which was not possible with Ray before, which can also further optimize performance and also express a complicated program like pipeline parallelism. And it also comes with the optimized scheduler. Like for example, when you have a lot of send and receive, this automatically schedule in a way you can avoid the deadlock. When you use Nickel and have a lot of send and receive, it's very common to have a deadlock. But then compile DAG automatically sorts all the send and receive in a way it doesn't have a deadlock. And then you also automatically overlap compute and communication, so you can actually compute while you're getting the result for the next batch. This is the benchmark result for the Ray compile deck. So comparing to the regular Ray core, it has about 20 times faster performance across different CPU-based workloads, and also 3 times faster performance for multi-node. And then when you send 40 megabyte GPU tensor through just regular Ray API versus compile deck, with NVLink, we can see it's about 140 times faster. And without NVLink, even without NVLink, we could see it's about 20 times faster compared to just regular Ray. So we wanted to leverage this feature for the new vLLM architecture. So we go back to original architecture that has a scheduler on the Ray driver, and then all the workers run the model. So there's no GL interrupting each other. So with the compile deck, you can actually remove the huge Ray overhead, and you can have very small overhead, such as 100 to 200 microseconds. And then also, we added another optimization in vLLM to send only the delta input. And at the end, we could see there's less than 1 millisecond overhead in general for sending a data. We can also implement, since the compiled graph supports the GPU to GPU transfer, we could also implement tensor parallelism and pipeline parallelism with it. So for tensor parallelism, you can simply implement it by just running all the workers at the same time. Because it's SPMD, you just need to run the same code. And for pipeline parallelism, you can leverage the GPU to GPU RDMA feature. So first, you send the input to all the workers with low CPU overhead feature. And then you prepare you execute the model on first 2 stages. So this first 2 stage has also tensor parallelism. That's why there are 2 workers. So it's a 2D parallelism. And then for pipeline parallelism, you have to send the intermediate activation to the next layers. This can be implemented using the compiled graph, the nickel RDMA. And then for the second stage, you can just execute the model with the activation transferred. So this is the kind of like pseudocode for pipeline parallelism. So you first have an input, which is going to be a batch of prompt. And then for each pipeline parallel stage, you run the tensor parallelism. So you have to run the same code on multiple workers. And then when it's not the last stage, you just send the intermediate activation to the next stage through nickel. And you can specify how to use nickel in compiled graph using this API. And we performed the benchmark with the new architecture. The new architecture is not completely settled down, but we're planning to make it the default implementation for Ray backend. We can see generally it reaches the performance parity with the default control plane that uses the nickel broadcast for like speculative decoding, tensor parallelism, throughput, and latency. And one thing to note is that default control plane was very highly optimized. It has a lot of optimization to make CPU transfer faster with the nickel broadcast. But then the compiled graph can achieve the same performance without any additional code there. And also, we could see the better pipeline parallelism performance because now scheduler and the first worker is decoupled, and then pipeline parallelism tends to have a more complicated scheduler. And we could see generally 10 to 20% improvement on latency benchmark for 2D parallelism on a single node on 800. And in Anyscale, we also run the batch inference with L4 GPU, which doesn't come with NVLink. And in this kind of case, we saw pipeline parallelism actually has a better performance compared to tensor parallelism. And we use PP8 for our the batch inference workload. And then for PP8 workload, we also could see a 10% improvement in the performance. Okay, let's conclude the talk. So vLLM supports various parallelism strategy to support large language model inference. And it also comes with a low overhead control plane, which comes with a lot more features on top of what I just presented. And then vLLM is going to leverage Ray compiled graph to support low overhead architecture. And also it can also improve the pipeline parallelism implementation. Okay, thank you so much. That's all for our talk. And
Great.
Yeah, so compiled graph is in active development. So if you're interested in the feature, join the Ray Slack and join Ray Accelerated Tech channel. It was the old name. Now it's renamed to compiled graph. And then Anyscale is also hiring. So if you are interested, please let me know.
All right. Any questions for the wonderful talk and the speakers? If you can raise your hand if you have questions. Yes, we have 2 questions down there.
Yeah. So just wondering, like, if in Ray ADA, can we send message like in an out of order manner, so that basically the send order and the receive order doesn't match?
So this one, the compiled graph automatically resolve the ordering. So if you follow the API, so if there's a deadlock in your code, then it raises an error. And if it's working order, then it's automatically ordering. It runs the topological sort and makes sure there's no deadlock. So your send and receive order is always correct.
Yeah, so after you do the redeck and compile, so you move to the original design. So rehead and rework, they are on the different VMs. Did you try rehead and rework still on the VMs? They are on the different processor, so which maybe can also avoid your problem.
Oh, sorry, can you just repeat one more time? Yeah. Yeah.
Yeah. So the last presentation, right? You have the rehead and reworker on the different machines. So did you try the rehead and reworker on the same machines, but on the different processor?
Oh yeah, that's right. That's right. Same machine on a different process.
Yeah.
Yeah.
Did you try that?
Oh, that's how it works now.
Okay.
Yeah.
It's not on the different VMs.
Oh yeah, it's not on different.
Okay.
Yeah, that's right.
Question. Can we pass this over, please? Thank you.
Hi, could you provide more guidance on using tensor parallelism and pipeline parallelism together? Like in what cases might it make sense for either like latency or throughput?
Yeah. So I think I briefly mentioned earlier, but kind of the general rule of thumb, so to speak, is you want to use tensor parallelism within a node, which is why like already default vLLM just with tensor parallelism already so powerful. Because let's say you have like 8 GPUs on a node, pretty good, like I guess with 8 H100s, pretty good to serve most of the models nowadays. Pipeline parallelism is really when you're in a communication like constrained kind of mode, right? So that comes kind of automatically in a multi-node case because in general, a communication across nodes is going to be worse than within a node. But then you also have cases even within a node where you might not have NVLink, right? Let's say you're using like L4s or A10s, basically cheaper GPUs that don't have the like NVLink or better networking solutions. That's where you would, pipeline parallelism could also be effective. So it's just this like balance between the communication overhead and then the latency basically. Does that answer the question?
Yeah, I guess like for my own sanity checking, so like if I wanted to put like a 400 billion model on 2 nodes,
Yeah.
I would put like tensor parallelism 8 and then pipeline parallelism 2 because there are 2 nodes.
Exactly, yeah, and this is how it's done. For example, 405B serving at Snowflake is done in this 8x2 way, yeah, with BF16.
Thank you. Got more questions? All right. Excuse me. If I pass this over.
Hi. You talked about hosting Llama 405B across nodes, but it still feels like you're bottlenecked by nickel. Am I right in that sense? And is there any research on like on the hardware level communication protocol between like multiple nodes that Anyscale is focused on?
Sorry, could you repeat like the first part again?
So the communication between the nodes is still bottlenecked by nickel, right?
Yes.
Is there any research by Anyscale on that part? But
So you're saying communication is still bottlenecked by nickel, and is there any research in Anyscale to improve performance?
yes, that's
My answer is no. But I think nickel is already pretty good for many cases. And then when you're in the single node with NVLink, it's really fast. I think when you're actually multi-node, and then if you don't have the direct RDMA hardware, then it can be really slow because it's using, I think, TCP under the hood. I think there are a lot of researches out there that how to optimize performance in this kind of scenario with more like a slower network. But then Anyscale, we don't have any specific work right now.
Cool. Given the time constraint, please ask the speaker once we finish this session. And again, please give a round of applause for the speakers.